So we'll take up our quiz. So this was the first question, it was a sketching question. I gave you the function, and I gave you the derivative and second derivative functions as well. We just need to sort of interpret everything and make a graph of it. So when I say everything, I mean like everything. So this says, find the domain and range, x, y intercept, sign of the functions, vertical and horizontal asymptotes. And this question we can all do just using the function. We don't need the derivative or the second derivative yet. This will be for the derivative, and that will be for the second derivative. So x and y intercepts are pretty easy to start with. So to find your y-intercept, just set x equal to 0 and figure out what y is. Well, if x is 0, we're just left with negative 3 over 2. So negative 3 over 2. And we can do the same for our x-intercept. If y is 0, so set your function equal to 0, and then you're just looking at when 2x minus 3 is 0, right? Which happens at 3 over 2. You can just rearrange that equation. All right, let's look for vertical and horizontal asymptotes. So vertical asymptotes, I'm just going to call VA, vertical asymptotes. Okay, so to find vertical asymptotes, you're going to look at the denominator and look at when it's not going to be defined. Or when the denominator equals 0, so the function is not defined. And that's going to happen when x equals negative 2. So when x equals negative 2, we have a vertical asymptote. Well, what about a horizontal asymptote? To find that, you're going to take the limit as x approaches infinity. And what's going to happen is, I'll do this over here. So you'll end up with the limit as x approaches infinity. You'll pull out your highest order of x. So we'll have 2x times by 1 minus 3 over 2x all over x times by 1 plus 2 over x. So now you get 1x canceling. When you take the limit, the bracket goes to 1, and we're just left with 2. So we get a horizontal asymptote at y equals 2. You've probably done this enough by now, so you might be able to see right here, if you have the same order of x on the numerator and the denominator, you just take their coefficients and divide them. So you can probably do that without writing a whole bunch of limit steps, right? You have 2x and x, so 2 over 1, 2. All right, so we do need to see the signs of the functions and the domain and range, and we're going to do that by looking at where these functions, or how these functions act near their asymptotes. So let's start with the vertical asymptotes. We're going to find the limit as x approaches negative 2 from the left for the function, and we're going to find the limit as x approaches negative 2 from the right of our function. So as it approaches from the left, you can just take a number close to negative 2, but on the left, like negative 2.001, right? Substitute that into your function, and you get a very, very large number, which means this is going to approach positive infinity. You can do the same thing from the right, negative 2. So like negative 1.999, plug that into the function, you get a very large negative number. So this is approaching negative infinity. All right, what about our x-asymptote? We want to know where it's coming from above and where it's coming from below. All right, so as x approaches positive infinity, you can just take a very large number like positive 1,000 and check it. And what happens is when you plug in positive 1,000, you get a number that is less than 2. So that means it's going to be approaching that from below. All right, well, what about when we have negative 1,000, right? As x becomes very, very large negatively, we end up with a number greater than 0. Greater than 2, which is where our horizontal asymptote is. So we're approaching that horizontal asymptote from above. Next, extreme values. To look at extreme values, those are our maximum, minimum. We need to look at the derivative function and see when does this equal 0. And that never happens. We don't get a horizontal tangent. Not in this case anyways. So, that's easy. None. Alright, what about points of inflection? Well, you can look at this, our second derivative, to find any points of inflection. And you can see when we set that equal to 0, well, we can get an answer of -2. But that's where our vertical asymptote is. So we're not going to have a point there, but we can certainly test for concavity, either on the left side of that vertical asymptote or on the right side. We can see whether or not it's concave up or concave down. So let's do both those tests. Let's look at when x is less than -2. And let's look at when x is greater than -2. So we're going to test the function. So our second derivative function, when x is less than -2, just take any value you want that's less than -2, and you get a positive value for your second derivative function. So that means we are concave up at this point. If you take a number greater than -2, test that inside of your second derivative function, and you get something that is less than 0. So therefore, we are concave down. So now we have everything we need to be able to sketch the function. So let me draw some axes. So there's x and y. Let me put in some asymptotes. So here we have an asymptote at -2. Kind of slanted, but it should be straight. And we have a horizontal asymptote at +2, like this. Okay, now if we are on the left of this horizontal asymptote, right, we can see that coming from the left, we approach infinity, so up here. And we come to the horizontal asymptote from above. So over here, it looks like this. Okay, now we also have our intercepts. So we have our y-intercept somewhere here, and our x-intercept somewhere here. As we approach the horizontal asymptote, we approach it from below, right? Because it's less than 2. So we approach it from below over here. And as we approach the vertical asymptote from the right, right, we go to -infinity. So it looks something like, that should have gone through the intercept, but something like that. All right, here we go. So in this optimization question, we have 3 people building a shed in the shape of a rectangular prism. The volume of the shed is given by, so I'm already giving you the function for the volume. I'm not asking you to use any volume equations to determine that yourself. Where x is the height of the shed in meters, so it's already in terms of height. And between 0 and 4, so I give you the domain as well. So I give you a lot in this question. It's a nice, simple question. So it says, determine the height of the shed that has an absolute maximum volume. So if we want to find a maximum volume, well, that means we want to find where this derivative equals 0. And then we have to test, because it could be a minimum, right? So we have to test to see if that's a maxima or a minima. So let's first start by finding the derivative. So v prime of x is going to equal, I'm going to start with the higher order one, so 6x squared minus 54x plus 108. All right, now I set that equal to 0. This was actually nicely, we can factor this nicely. So we'll start by pulling out a 6, and we get x squared minus 9x plus 18, which equals 0. And that factors out nicely as well. We'll get x minus 6, and x minus 3. So we get a couple of values here. X could be 6, x could be 3, but also look at your domain. X could be 0 because our maximum could be on the endpoints, or x is 4. Now, x equals 0, we know that's not going to work. We plug in 0 in for x, we're going to get a volume of 0. So we can immediately cancel that one out. But the other values we're going to have to test. So let's do that. Let's test what the volume would be at 3. So if we sub in x is 3 into our volume equation, we get 135 meters squared. Right? So maybe let's try 6. If we substitute 6 in there, right, into our volume equation, we're going to get 108 meters squared. Okay, so 3 is definitely larger, so not 6, but we still need to test that endpoint. So if we sub in 4 into that volume, we get 128 meters. Oh, this should all be cubed. It's volume. Okay, so where is volume maximized? Not here and not here. The volume is maximized here when the height of the shed is 3 meters. So you can just write a therefore statement. A height of shed, or height of 3 meters, gives maximum volume. Of shed.